This activity is meant to start with a geometric series and see how we can take that geometric series and use it as an expression for a function. And so we start with just a quick review of a geometric series. Remember, a geometric series is where you have a constant times a common ratio to the nth power. And if we want to talk about finding a sum, we have to make sure that we start summing from the 0th term all the way out to the infinite term. And then that sum is the ratio a over 1 minus r. So if we look at this, we can see that our first term is a, and our common ratio is 1/3. So we multiply 9 by a third to get a 3, multiply 3 by a third to get 1, and so on and so forth. And we can find the sum here. Our sum here is a over 1 minus r. Our sum happens to be 9 over 1 minus a third, which is equal to 9 over 2/3, which equals 9 times 3 halves, which is 27 halves. When we talk about geometric series in general, the restriction, if you remember, is the absolute value of r has to be less than 1. In other words, we have to trap r between -1 and 1. So this common ratio has to be something that causes these terms to get smaller and smaller and smaller. And so it's this that really then describes a family of geometric series. So we can look at that and say, well, we have all of these geometric series where common ratios are trapped between -1 and 1. We know that we have a converging geometric series, and we know we can find a sum. So if we kind of take that that philosophy and look at this expression, 1 minus x squared plus x to the 4th minus x to the 6th, and so on and so forth. We take a look at that, and from a geometric series standpoint, we see something like that, and I'm just kind of looking at these questions right here, 3, 4, and 5. We can continue the pattern by adding another term, so that would be plus x to the 8th, and we can continue the pattern again by adding yet another term, which would be minus x to the 10th. And so if we look at this, then we have a first term, which is 1, and in this case, a common ratio here, which happens to be minus x squared. So if we think about that sort of pattern, we can see that this polynomial expression can be graphed. And so if we graph that polynomial expression, let's get the graphing calculator out here. Okay, if we graph that polynomial expression, then we're looking at 1 minus x squared plus x to the 4th minus x to the 6th. If we just start there, that's this expression here, that's y1, and we graph that, we get something that looks like that. Okay. If we then add that next term, so in this case, we get y1, and to y1 we add x to the 8th power, and we'll make it thick. We get something that looks like that. So it looks kind of like a W. And then if we add to that another term, so we take y2, and add, or subtract, I guess, x to the 10th power. We end up getting that, and we can see that that's just a little bit skinnier. And so we can keep going back and forth on this. So if we, let's just take this out one more term. If we take y3, and add another term to it, so it would be plus x to the 12th power. And I think I'm going to change the weighting on this. I'll make this a heavy one, that a heavy one, because one goes up and one goes down. That a light one. There we go. And then we graph that one. We get a W shape again. There's the first upside down U. Then we get the W shape here. Then we get the skinnier U shape next. There it is. And then we get the skinnier W shape. Coming down from the top. There it is. Okay, and so if we zoom in on that, maybe our x-min is -3 and our x-max is 3, and maybe -5 and 5. Then we can see it, that's the y1, the y2, so we can start to see the, there's the y3, and here's the y4. There we go. We can start to see that we have this oscillation between, we have our y1 here, and then our y2 is this skinnier one here, then our y3 is here, and our y4 is here. So you can see that we start to oscillate between above and below. Oops, let me try to write that consistently. y4. There we go. You can see we oscillate from below to above, and we oscillate from this U-shaped thing to this kind of W-shaped thing. And so as we continually expand this, we start to see that we get this area in the center here where the functions seem to match up real well, and then we get these areas above and below where the functions don't seem to match up real well. And so if we take a look at this, we see our first term is 1, we see our common ratio is negative x squared. And so if we look at this from a geometric series standpoint, because this is very geometric, we have an obvious first term and an obvious common ratio. If we write the expression for the sum here, which is a over 1 minus r, we're taking a look at 1 over 1 minus the common ratio, which is a negative x squared. So we see that the sum then is 1 over 1 plus x squared. And if we take a look at this function here, if we take a look at this sum here as a function, so that expression for the sum here, 1 over 1 minus, or excuse me, 1 plus x squared as a function, we'll call it g of x here, and we'll graph it in y5. Actually, I'm going to graph it in y6 because y5 was up here in the instructions. I'll graph it in y6. So if we come back here and graph that in y6, 1 divided by the quantity 1 plus x squared, then we get something that looks like this. So if you notice that and we'll turn that off. We'll turn these guys off just for a second so we can get that picture. There we go. So if we look at that, we see that we have just that portion of the graph here that follows that same contour that we have up here. So when we look at this, we look at these polynomial expressions that they follow the value of this function. They follow the value of this, and this is a non-polynomial. Okay, and so they closely mimic this non-polynomial function that represents the sum of the infinite series. This polynomial function matches it for a period of time, and then after which it kind of goes off and behaves in its polynomial way. But so the idea then is, if we were to extend this, so if we were to write more and more terms, if we were to put in a y7 here that was 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus minus x to the 10th plus x to the 12th minus x to the 14th plus x to the 16th, and so on and so forth. Then we start to get this really high degree polynomial, and all we're doing is we're adding up the next terms. So the sum of this has got to equal 1 over 1 plus x squared. And so this non-polynomial function can then be approximated by however many terms we want to go out to in this polynomial approximation. So we have this, and if we can just review the definition of a polynomial, we have this polynomial partial sum, so we call it an approximation. And we call it an approximation because it's not an infinite sum, it's finite. And polynomials are, of course, x terms raised to some positive power. And so that polynomial approximation is going to match this non-polynomial function for a period of time. It's, you'd have to write out infinitely many terms to get an exact match. So the idea is then, can we use a polynomial approximation for, 200 or 300 or 400 terms that would be sufficient rather than using this non-polynomial function? And if so, how far would it match? And so if we go back to our definition of a geometric series, and we kind of look at the graph to see where this graph lines up with the polynomial approximations, which I'm going to turn back on now. We can see that those polynomial approximations match up pretty good in that area from -1 to 1. Just like that criteria that we had set for geometric series for convergence. So we know that when we have these values from -1 to 1, we get some pretty good matching. And so then, we take a look at this and we say, well, are there other non-polynomial functions that we can do this with, that we can approximate with polynomial expressions? And the answer to that is, yeah, there's lots of them that we can use polynomial approximations for approximating these non-polynomial functions. So if we look at this sum, which is definitely non-polynomial, and we think of this function as a sum for a geometric series, let's try to get it into this form. So if we remember about what we know about the sum, is this has to be a constant. And then this ratio really can be just about anything. And that's going to be a function of x, and we have to have the minus sign here. So if we start out with x over x minus 1, and to get this to be a constant, we can divide the top by x, and we can divide the bottom by x. So that gets us 1 over, and then this is x over x minus 1 over x. So if we simplify that, that's 1 over 1 minus x, so that fits our our expression for the sum. We have a constant here, our a is equal to 1. We have the 1 minus here, that's important, and then the common ratio then is 1 over x. So we're looking at this then as, if we write this in series form, n equals 0 to infinity, 1 over x to the n. So we're looking at approximating this then. If we would write this out as a sum, we would start with 1, and then the next term would be 1 over x, and the next term would be 1 over x squared, and 1 over x cubed, 1 over x to the 4th, and so forth. So we're going to write the first 5 terms of the series, graph it in y1. So let's go ahead and get the first 5 terms of that series graphed so we can clear this stuff. Okay, so the first 5 terms, 1, 2, 3, 4, 5, would be this expression here.
So what I have put into the graphing calculator over here is the non-polynomial function, 1 divided by the quantity 1 minus 1 over x. And that is this right here, which is what we are calling the sum of the series, and I have it graphed in this form right here. And then in Y2, I have the approximation here graphed. And so when we look at the approximation and the sum, we can see here's the non-polynomial function, the 1 over 1 minus 1 over x. And then here comes the the approximation. Notice so the approximation goes up there, but then follows this portion of the curve pretty closely. And it goes up here because we have a 1 over x to the 4th polynomial here. So if I would approximate this by adding another term here, so if I would approximate this by saying, just continuing this approximation and saying 1 divided by x to the 5th power, and regraph it here, again, the thick curve is the non-polynomial function. Here comes the approximation, and we'll now see that approximation follow a little more closely both sections of that graph. And so as we look at this, and if we would add an x to the 6th term, we would see that this would flip back up here again. And so we'd get on this portion of the curve, we get that flipping up and down as we continue the approximation, which isn't too concerning, because really when we're talking about an approximation, we're talking about the values of n as n goes from 0 to infinity, which really encompasses this part of the graph anyway. So that's really our area of concern. And so as you can see, this matches pretty closely. It starts matching up about here pretty darn close. Likewise, it matches here pretty close. So we're looking at this this section here where it matches close, and that's about maybe greater than 1.5 or 2. So for an x of greater than about 1.5, it matches pretty close. For x less than about a negative 1.5, it looks pretty close. And as we add terms, more and more terms, this will start to match closer and closer. And so that area where we start to see this matching closer and closer, we call that interval of convergence. And so right now it's looking to be approximately less than negative 1.5 and greater than 1.5. If we added a couple hundred terms out here, these numbers would tend to get closer to 1. So that interval of convergence ends up being looking like that, where it converges for everything less than negative 1 and everything greater than positive 1. And that just depends upon how many terms you want to take it out to. If we take a look at this, and this is just a little bit of an exploratory exercise here. We'll clear out all of this stuff. If we take a look at this expression, we have x minus x cubed divided by 3 factorial. The factorial is underneath math under probability, so we do have a factorial function there. And then plus x to the 5th divided by 5 factorial. So if we look at that approximation, looks something like this. Okay, and as we, so it's a typical 5th degree polynomial. If we, oops, I missed a minus sign here. This should be a minus sign here. There we go. Looks like this. Again, typical fifth degree polynomial where it goes down on one end and up on the other. And and so there's, a real typical fifth degree polynomial. If we start extending this, so if we look at this pattern here, we see that we have odd powers. So the next one would be x to the 7 over 7 factorial. And then we alternate minus plus minus plus x to the 9th over 9 factorial minus x to the 11th over 11 factorial plus dot, 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 dot. So if we start to show some of those next approximations, I'll go ahead and grab y1, and then to that I'll subtract x to the 7 divided by 7 factorial. And we'll take a look at that. And so x to the 7 divided by 7 factorial, if you notice, comes in from above, but then follows this pretty closely, and then goes down. So we just kind of came in, it kind of almost reflected this over the x-axis. And if we add another one, so I can go ahead and grab y2 and add plus x to the 9th over 9 factorial. And if we look at that, that comes in and then starts to follow the other two functions real closely, and then comes out here. So we have something that looks like this. And then if we do that one more time, so I'll grab the y3, and then to that I'll add, subtract x to the 11th divided by 11 factorial. And, oops, I forgot a 1 there. X to the 11th divided by 11 factorial. There we go. Then we'll start to see the x to the 11th x to the 11th divided by 11 factorial coming through here. And so you can kind of see that as we get to higher and higher degrees in this polynomial, we start to see it spread out along the x-axis more and more with this oscillating pattern here. And by now you might have an idea of what that looks like. I'm just going to go ahead and turn off the lower degree polynomials so we can look at the 11th degree polynomial by itself. But if we look at that 11th degree polynomial, we start to see this oscillation here that comes up through the origin and back down. And then it looks like it starts to try to curve back up again, but that's where the degree of the polynomial takes over. So if we can, graph this again, we'd start to see, so here's our 11th degree polynomial. And if we would, so this is the x to the 11th, this is the 11th degree polynomial. So if we would graph the 13th degree, we can kind of see this hump here that's starting, that would tend to come down and then follow, and it would complete this hump up here, and that would be the 13th degree. And so as this is going on and on, you can see how it keeps laying down this oscillation. So what does that look like? Well, what do we know that oscillates like this and goes through 0? That would be our sine of x. So this approximation here then is, as we take it out more and more terms, it starts to match up with the sine of x. When we talk about the interval of convergence here, the farther you go out, the more it lines up exactly with sine of x. So it's going to converge everywhere. So when we say it converges everywhere, we say it has an infinite interval of convergence. If I'd come back up here and differentiate this then term by term, this would be a 1. This would be 3x squared over 3 factorial. Except it would be a minus there. And then differentiating this would be 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial. And so as we reduce that, let's just go one more, plus 9x to the 8th over over 9 factorial, excuse me. When we reduce this 3 over 3 factorial, we end up with a 2 factorial in the denominator. So it looks like x squared over 2 factorial. This cancels out with this 5, so we end up with an x to the 4th over 4 factorial. The 7's cancel, so we end up with an x to the 6 over 6 factorial. The 9's cancel. We end up with an x to the 8th power over 8 factorial. And so when we graph this, you might kind of get an idea of what we get here just by coming back here. And if this approximation represents this series, and this is the derivative, so this is an f prime of x, this is an f of x, then what's the derivative of sine of x? We end up getting cosine of x. So if we look at this, and we'll just take off that, and come down here and go ahead and graph 1 minus x squared divided by 2 factorial, which is just 2, plus x to the 4th divided by 4 factorial. Minus x to the 6th divided by 6 factorial. Plus x to the 8th divided by 8 factorial. And we take a look at that, then we start to see that it goes through now we start to see that cosine pattern where it intercepts the y-axis at 1. So we have this that point 0, 1. So we start to see this cosine sort of behavior.